talk about the microcytic anemia. So microcytic anemias are all the cases where the mean corpuscle is below 80 femtoliters. So microcytic anemia or anemias under 80 femtoliters, and basically we have four basic types, four main ones. And first one is sideropenic. Penic means low amounts of iron. Panic anemia. Or in other words, iron deficiency anemia. Then we got anemia of chronic diseases. Then we have sideroblastic anemia, and then we have thalassemias. And in case of sideropenic anemia, the main problem is decreased amounts of iron in the body. And on a comment, every time there is a sideropenic anemia and it's in a person above 50 years of age, this is very dangerous because this could be a sign of colon cancer. So you always scope them. Always. If you have like if you lose 5 milliliters of blood per day, you will get sooner or like later iron deficiency anemia. So remember, all the people with sideropenic anemia, scope. Find the cancer first. There's a very high probability. So what you're gonna do in case you think it's a sideropenic anemia? Well, you're gonna you're gonna do the iron studies, and you're gonna check the amount of level in the blood of the iron. You're gonna check the ferritin level, which is gonna be low, because you know ferritin tells you about how many iron you have in the cells in the body. It's approximate. And also what's going to be increased is total iron binding capacity, or in other words transferrin, because the body has no iron and is very hungry to get the iron. Watch out, ferritin, although people have sideropenic anemia, they have small erythrocytes, ferritin can be like in 1/3 of the patients can be normal. And this is why, well, it's because ferritin is also an acute phase reactant, and this could mask the actual absolute decrease of iron. So that's why watch out, in 30%, although they will have normal ferritin levels, they could be actually deficient. Another interesting sign is that as you're getting more and more anemic, and as you have less and less of iron, the erythrocytes will get smaller and smaller. So and the newer the erythrocytes, the newest produced, they're smaller and smaller. So also there is a increased red cell distribution width. That means that if you do a blood smear, they're going to be different sizes for erythrocytes. They're going to be smaller ones, even smaller, and different width. Okay, very wild widths, but all of them are going to be smaller than normal. One other interesting thing is it's a sideropenic anemia. So I'm having anemia. So of course the signal from kidney is going to be increased erythropoietin, and actually erythropoietin can work also on platelets a bit, so or on megakaryocytes. So that's why in case of sideropenic anemia, sometimes we see also increased platelets, and that's due to increased erythropoietin. So this is sideropenic anemia. Then another example are anemias of chronic disease, and basically the main player in this case, because those are chronic diseases like systemic lupus or cancer, it's increased hepcidin. And as we learned in the first videos in the iron metabolism, hepcidin blocks the opening of the ferritin. So basically, if I have increased levels of hepcidin and it's acute phase reactant, the iron's going to be locked in the cells. It's going to be locked in macrophages. It's going to be locked in hepatocytes and in the gastrointestinal enterocytes and everywhere where the ferritin is. So that's why actually, in case of although maybe levels of iron are high in some cells, functionally it's again a decrease of iron. But in contrast, with the sideropenic anemias, the iron is locked in the cells, and that's why there are going to be high levels of ferritin in the cells, and also then some of the ferritin will get into the blood. It will be high in ferritin's going to be high in the blood, and because we have lots of ferritin and lots of iron, also the hunger for the iron actually is going to be decreased. So total iron binding capacity is going to be decreased in the anemia of chronic diseases. Also, transferrin is going to be the same, decreased. Okay, and of course the only cure for this is to treat the original disease. So it's the systemic lupus. Then another example is sideroblastic anemia, and this is a very exceptional. Over here, there's lots of iron in the body, and it's locked in mitochondria. So there's lots of iron in the body, and also in the blood, but it's locked in mitochondria. And basically, you can have inherited forms, so some mutations, but the most common form is acquired. And remember alcohol. That's the magic word. The most common cause of sideroblastic anemia is alcohol. It could be lead, it could be chloramphenicol, or it could be chlorambucil, or it could be isoniazid. Let's say antibiotic for tuberculosis treatment, but the most common is alcohol. Okay, and watch out. Alcohol is the most common cause of sideroblastic anemia. So the problem is in mitochondria. There are sideroblasts present in the peripheral blood, and they have lots of iron in them. Okay, and interestingly, in this case of sideroblastic anemia, the erythrocytes are small, but you can do a special test. This is very diagnostically important, and you can do a special staining with Prussian blue. And if it is positive, it is very likely sideroblastic. And the erythrocytes, which are very small, they have a nucleus, and there is a. Normally, you shouldn't have erythroblasts in the peripheral blood smear. Over you have, and the Prussian blue will stain the mitochondria and the iron in it, which like circles around the nucleus. So remember, this is a special thing. Prussian blue test is very important with a sideroblastic anemia. A common alcohol, watch out. Alcohol is very diverse in its effect on blood and erythrocytes. So this is one example what alcohol can do. Alcohol can cause sideroblastic anemia. But not only this, alcohol can cause also macrocytic anemia, and also also megaloblastic. And basically in macrocytic anemia, the function of the alcohol is toxic. It's toxic directly for the bone marrow. Okay, so the alcohol toxicity on the marrow will cause macrocytic anemias, and in case of people overusing alcohol, you can have also decreased levels of B12 and folate. And in this case, it's due to, because they're drinking only alcohol, it's due to the lack in the food. So basically, this is gonna cause, although they're using lots of alcohol, it's not, again over here, it's not the toxic effect on bone marrow, but just that they don't get it. So this would be megaloblastic anemia. We're going to talk about it in a second. And last example are thalassemias, and you have two types, and over here it's a totally different problem as we talked about already. The problem is deletion of the alleles for the alpha or beta chain. So in case there is alpha chain missing, it's called alpha thalassemias. If there is beta chain missing, it's called beta thalassemias. But as we talked previously in more detail about hemoglobin and thalassemias, over here we care mainly about the 3 deletion type, because if you have 4 alleles, and first type is very light. It's like a silent thalassemia. If you have deletion of 2 alleles, it's a very minor anemia. There are small erythrocytes, but it's not so important. It's sort of you call it a trait or thalassemia minor, alpha thalassemia. But you care very much about the 3 deletion, which is a severe anemia where transfusion is needed. Over here, of course, also spleen is going to be increased because there's an increased destruction in the spleen. So the spleen is going to be bigger, and a hallmark of this 3 deletion thalassemia alpha is a ABH hemoglobin, and also the BARTs. But in most cases, it's the beta 4 tetrans hemoglobin, which is the most important. So there are 4 beta chains together. So ABH is very important. Basically, to tell apart 1 deletion and 2 deletion thalassemias, you need to do genetic testing to find it out. It's very hard to tell. But with this severe thalassemia, check the ABH and the blood smear, and if it's increased, it's very likely that version. 4 deletion of the alleles for alpha chain is lethal, so you don't have to care about that one. Okay, and the other type is beta thalassemia. Again, if it's a heterozygous, because we got only 2 alleles, there's only 1 gene for beta chain. So 1 deletion, it's a heterozygous, it's a trait, it's a minor thalassemia, minor, not like it's pretty fine. But when there are both 2 deletions of the both alleles, then it's a severe anemia again, and hallmark is increased hemoglobin F. In this case, that's the most important. So if you check, and this one's going to be increased, it's very likely beta thalassemia, and even more important, and this is like real hormone, is the hemoglobin A2. So this is this can be present or not, but hemoglobin A2 is the most important hallmark for beta thalassemia major. Interesting with thalassemias, if you do the iron studies, everything. So iron's gonna be normal, ferritin is gonna be normal, and TIBC total is gonna be normal. So that's a hallmark for thalassemias. Also, I forgot about the iron study. So over here in this sideroblastic situation, so if it's sideroblastic anemia, in contrast to these two, iron's going to be actually higher in the blood. So iron level is going to be higher. We have lots of iron in the cells. Ferritin's going to be high. Okay, and also the total iron capacity is going to be decreased. Transferrin. So this is about microcytic anemias and how you can tell the difference. Look at this: decreased iron, increased iron, and normal iron. Ferritin decreased, increased, lots of ferritin in the cells, also lots of iron in the cells and ferritin, and normal. And total iron binding capacity, all of if there is not enough iron, they're hungry for them. Over here, they're not hungry; they have lots of it. Okay, so that's that's all for microcytic anemias. So, thanks for watching, and don't forget to subscribe and ring that bell. And as always, Check the description below for supplementary questions and other materials.